Hi, I'm Ioana Bica and I'm a PhD student at the University of Oxford and the Alan Turing Institute. In this tutorial, I'll talk about estimating the effects of continuous valid interventions from observational data using generative adversarial networks. So, as we've already seen as part of this tutorial series, estimating the personalized effects of interventions is crucial for decision making in domains such as medicine. For instance, in this illustrative example here, we consider a patient with breast cancer for which we have diagnostic information such as tumor size, number of positive nodes, HER2 status, and so on, and for each one to determine the best treatment option. We train machine learning methods for causal inference on observational data from electronic health records, where we have seen what has happened to other patients under various treatment options, in this case chemotherapy and radiotherapy. Then, these causal inference methods can be used to estimate individualized effects of these treatments on our current patient and then decide whether the chemotherapy or radiotherapy treatment is better for the patient. However, most of the methods developed in the causal inference literature focus on learning the counterfactual outcomes for discrete interventions such as binary or categorical treatments. However, in many scenarios such as healthcare, deciding how to intervene involves not only deciding between different treatment options, such as chemotherapy or radiotherapy, but also deciding on the value of some continuous parameter associated with the intervention, such as the dosage of the treatment. In the medical setting, using a high dosage for the treatment can lead to toxic effects, while using a low dosage can result in no effect on the patient outcome. In other domains, there are many examples of continuous interventions, such as the duration of an education or job training program, the frequency of an exposure, or the price used in an advert. Naturally, being able to estimate the effects of these continuous interventions will aid in the decision-making process. Our aim is to learn from observational data such as electronic health records, which contain information about patient features X, the factual type of treatment WF, and corresponding factual dosage DF assigned to them. The pair WF-DF represents a factual treatment TF. Moreover, we also observe the factual outcome YF for the received type of treatment W and dosage D. Following Rubin and Neymann's potential outcomes framework, we assume that for all treatment dosage pairs W and D, there is a potential outcome, and our aim is to estimate the individualized dose response curves, which contains all of the potential outcomes, both factual and counterfactual, given the patient characteristics. Now, to be able to identify these potential outcomes from observational data, we need to make the following two assumptions: overlap and no-key-end confounders. Overlap means that each time step there is a non-zero probability of receiving each treatment dosage pair for each patient. And no-key-end confounders means that we observe all patient covariates that are affecting the treatment assignment and the patient outcomes. This is needed to be able to correctly adjust for the confounders when estimating individualized treatment effects. Nevertheless, having no-key-end confounders is a strong assumption and cannot be tested in practice, and because of this, domain knowledge becomes vital to assess the validity of this assumption. Learning from observational data already presents significant challenges when there is only a single discrete intervention, and thus the decision is binary or categorical, where we need to choose between multiple treatments. This is because only the factual outcome is present in the data, and the counterfactual outcomes are never observed. This problem is exacerbated in the setting of continuous interventions, where the number of counterfactuals is no longer even finite. Moreover, the decision to intervene is non-random and instead depends on patient features, thus creating treatment and dosage selection bias. Due to the continuous nature of the interventions, adjusting for selection bias is significantly more complex than for categorical treatments, and standard methods for adjusting for selection bias in the discrete treatment setting cannot be easily extended to handle the bias in continuous setting. In our work, we introduced SAIGAN, which is a novel causal inference method that can be used to estimate the effect of such continuous valid interventions. SAIGAN builds on the framework of generative adversarial networks to learn the distribution of the unobserved counterfactuals. As illustrated here, the generator estimates the individualized dose response curves. We then define a discriminator that acts on a finite set of points from each generated curve and identifies the factual outcome from the set of factual outcomes and the generated counterfactual ones. The intuition is that if a counterfactual generator and discriminator are trained adversarially, then the generator can fool the discriminator such that it will not be able to correctly identify the factual outcome by generating the potential outcomes according to their true distribution. We propose estimating individualized dose response curves by first training a counterfactual generator using a min-max adversarial game to generate response curves for each sample within the training dataset. Then, once we have trained the counterfactual generator, we can use it to only access the generated dose response curves for all samples in the dataset. That's essentially creating a complete dataset with all of the counterfactuals. Thus, the learned generator can then be used to train an inference network using standard supervised learning methods. As mentioned, SAIGAN uses a modified GAN framework to generate potential outcomes, conditional on the observed features, treatments, and factual outcome. However, several changes must be made to both the generator and discriminator architectures and learning paradigms in order to produce a model capable of handling the dose response setting. We will now describe into details the various components of the GAN framework. The counterfactual generator takes as input the patient features X, the factual outcome YF, the received type of treatment WF and dosage DF, and some noise, and outputs the dose response curve for each type of treatment. Since it is not possible to give as input to a discriminator the entire dose response curve, we define a discriminator that acts on a random set of points from each of the generated dose response curves. Here, we describe how we get this random set of points to give as input to the discriminator. For each treatment W, we will compare NW dosage samples. In particular, for each treatment W, we sample NW dosage levels from the dosage domain. Then, we use a generator to obtain the counterfactual outcomes for the sample dosages for each treatment W, and we form the dosage outcome pairs as indicated here. Note that for the factual treatment WF, we replace one of the dosage samples with the factual dosage DF, and we use the factual outcome YF instead of the generated one. This way, we obtain the set of dosage outcome pairs for all treatment types W, and we give as input to the discriminator. This set of dosage outcome pairs contains the factual outcome YF and factual dosage DF for the factual treatment type WF from the observational dataset, and the counterfactual ones from the generator for the sample dosages for each treatment. Our discriminator will take the patient features X together with a random set of generated outcomes Y and output a probability for each treatment dosage pair, indicating the discriminator's belief that that pair is a factual one. This will give us the GAN loss described here for training the generator. Now, while the job of the generator is to generate outcomes for the treatment dosage pairs which are not observed, we notice that its performance is improved by adding a supervised loss term that regularizes its output for the factual treatment dosage pair. So the overall min-max gain is described on this slide. Now the task of the discriminator, which is to pick out the factual dosage from NW dosage pairs for k different types of treatments, becomes increasingly difficult as we increase the number of dosage samples NW or the number of treatment types k, because the dimension of the discriminator output space increases significantly. And even though we can control the number of dosage samples NW, if we set it too low, then the set of dosage outcome samples YTD may not well represent the dose response curve, particularly if the dose response curve is complex. And in practice, we found that even for moderate settings of NW and only 2 treatments, modeling the discriminator as a single function resulted in poor performance. So in order to overcome this problem, we introduced a novel hierarchical discriminator which involves a treatment discriminator with output dimension k and several dosage discriminators, one for each treatment, each with output dimension NW. We will now derive how we build this hierarchical discriminator. First, notice that the probability that needs to be computed by the discriminator can be split into 2 as written on this slide. We can therefore break down the discriminator into a hierarchical model. So we can have a treatment discriminator that estimates the probability of each treatment from the set of dosage outcome pairs for all treatments. Then, for each treatment type, we can have a dosage discriminator that needs to compute the probability of each dosage. We illustrate here the full hierarchical discriminator. So the treatment discriminator on the left takes as input the patient features X and the set of dosage outcome pairs and outputs the probability for each treatment. It is trained using the treatment discriminator loss outlined here to identify the factual treatment. Then, for each treatment type, the dosage discriminator, illustrated on the right, takes as input the patient features and the corresponding dosage outcome pairs and outputs a probability for each dosage level. And during training, we use the following laws for the dosage discriminator, where for each data point, we train the corresponding dosage discriminator for the factual treatment to identify the factual dosage. Finally, the overall discriminator has the output for each treatment dosage pair as described here, where we multiply the outcomes from the treatment and dosage discriminators. We illustrate here the overall GAN framework that we use for SAIGAN, where the counterfactual generator and discriminator are trained according to the min-max gain described here. Another novel contribution of our work is that we provide theoretical results that justify using the GAN framework to learn to generate counterfactual outcomes. The theoretical results provided in our paper establish that our hierarchical GAN learns counterfactors that agree in marginal distribution with the true data. In particular, we proved that the optimal generator needs to learn counterfactors according to their true distribution. Please refer the paper for the full details of the proof. Once we have learned the counterfactual generator, we can use it to access generated dose response curves for all samples in the dataset. Now, to generate dose response curves for a new sample, we use the counterfactual generator along with the original dataset to train an inference network using supervised learning methods. And similar to the way we train the generator and the discriminator, we train the inference using a random set of dosages. And the loss for training the inference network is described here. Note that for the factual treatment and dosage, we use the factual outcomes from the observational dataset, while for the other sample dosages, we use the generated ones from the counterfactual generator. When I have described the architectures we use for the generator, discriminators, and inference networks. So for the generator, we adopt a multitask deep learning model that consists of a shared layer, and then for each treatment W, we introduce a multitask head that takes as input the dosage to produce the outcome. To ensure that the discriminators can act as functions on sets of the randomly selected dosage outcome pairs, we build them as permutation invariant and permutation equivariant neural networks. In particular, the treatment discriminator receives all of the sets of dosage outcome pairs, one set for each treatment, and outputs a probability for each treatment. That is, there is only one output corresponding to each set. Thus, to build the treatment discriminator, we treat each input set of dosage outcome pairs as a vector, but we require that the output of the discriminator to be invariant to the ordering of the elements in the set. On the other hand, each dosage discriminator receives as input a set of dosage outcome pairs corresponding to a given treatment, and it is tasked with outputting a probability for each element in the set. In order to define such a function for the dosage discriminator, we consider that the input and output as vector, but then require that if we permute the elements of the input vector, then the output should be permuted in the same way. And to do this, we use permutation equivariant layers to build the dosage discriminator. The inference network has the same architecture as the generator, but only receives as input the patient features, as these are the only thing we have access to when using SAIGAN on a new test patient. The inference network can then be used to estimate the individualized dose response curves for each patient. The nature of the treatment effect estimation problem, even in the binary treatment setting, does not allow for meaningful evaluation on real-world datasets due to the inability to observe all counterfactuals. While there are well-established benchmark synthetic models for the categorical treatment setting, no such model exists for the dosage setting. So we propose our own semi-synthetic data simulation model to evaluate SAIGAN against several benchmarks. We simulate data as follows. We obtain patient features X from a real dataset. In our paper, we use as real datasets TCGA, News, and Mimics3. We then consider 3 treatments, each with a corresponding dosage. Each treatment type W is associated with a set of parameters phi, which are sampled randomly for each experiment. The shape of the dose response curve for each treatment FW is given in this table here, along with the closed form expression for the optimal dosage that corresponds to the largest outcome. And note that the optimal dosage depends on the patient features. We then consider 3 shapes for FW to demonstrate learning heterogeneous response curves. The first curve can be broken down into 2 terms, a linear increasing term in the dosage D and a quadratic decreasing term in the dosage D. This first term could represent the improved efficacy of higher dosage of chemotherapy in reducing tumor size, while the quadratic term could represent the increased toxicity of chemotherapy as the dosage increasing. This type of trade-off presents itself in many other settings. We assign interventions to the patient in the observational data by sampling a dosage GW for each treatment from a beta distribution with parameters alpha and beta. The parameter alpha controls the selection bias, and we set beta according to alpha and the optimal dosage for each treatment. This setting ensures that the mode of our beta distribution is the optimal dosage and the variance is as described here. We see that the variance of our beta distribution decreases with alpha, resulting in the sample dosages being closer to the optimal dosage, thus resulting in higher dosage selection bias. We also know that for alpha set to 1, beta is also 1, and we thus obtain the uniform distribution corresponding to dosages being sampled independently of the patient features, thus resulting in no selection bias for the dosage. Given a selected dosage for each treatment, we then assign a treatment according to the categorical distribution described here, where increasing kappa increases the treatment selection bias, and kappa set to 0 leads to random treatment assignments. The factual intervention is given by WFDF, for which we simulate the factual outcome. Now for evaluation metrics, we use a mean integrated squared error, the dosage policy error, and the policy error. So we first perform ablation studies to investigate how each component of our model affects performance. We start with a baseline model in which both the generator and discriminator consist of a single fully connected network. Then, one at a time, we add in the following components in a cumulative way until we reach our full model. First, we add the supervised loss for the generator, then the multitask heads in the generator, then we add the hierarchical discriminator network, and then the invariance and equivariance layers in the treatment and dosage discriminators. The addition of each component results in improved performance, with the final row, which represents our full model, demonstrating the best performance across both datasets for all metrics. In terms of benchmarks comparison, we compare against the generalized propensity score, which is a GPS method here, and dose response networks, the DRNet methods here. As a baseline, we also compare against the standard multilayer perceptron, MLP, that takes patient features, treatment and dosage as input and estimates the patient outcomes, and a multitask variant, MLPM, that has a designated head for each treatment. Additional ablation studies and evaluation for the discrete dosage setting can be found in the paper. Finally, for the experiments, we illustrate here the model's robustness to increasing the treatment and dosage bias. We show the performance of the benchmark methods when varying kappa from 0, indicating no treatment bias, to 10, indicating strong treatment bias. Similarly, we show the performance for the dosage selection bias by setting alpha between 1, which is no bias, to 8, which is strong bias. SAIGAN shows consistent performance, significantly outperforming the benchmarks for all kappa and alpha. While our approach is very flexible since it accepts multiple treatments with corresponding dosages, one limitation is that SAIGAN needs at least a few thousand training examples, as it is generally the case with neural networks and especially GANs. Also, further work would consider how to incorporate prior knowledge about dose response functions, but also develop alternative methods for handling the continuous intervention causal inference setting. Moreover, extending the work to the temporal setting, where we have treatments with associated dosages in longitudinal patient trajectories, would also be important for medical decision-making. To summarize, in this tutorial we introduce SAIGAN, which is a novel causal inference framework that tackles a less studied problem of estimating the effects of continuous valid interventions. SAIGAN uses a significantly modified GAN model to learn to generate counterfactual outcomes, which can then be used to learn an inference model using standard supervised methods capable of estimating these counterfactuals for a new patient. As part of our contributions, we provide theoretical justification for using such a GAN framework to learn a distribution of the counterfactual outcomes. Moreover, we introduce a new semi-static data simulation to use for continuous intervention setting. And the reference for the paper can be found here, and the code for SAIGAN is publicly available, so please try it out. Thank you for listening.